Ionic bond. The elements of group 1 and group 2 being metals have the tendency to lose their valence electrons forming positively charged ions, whereas nonmetals of group 15 to group 17 have the tendency to gain or accept electrons. They are electron activity elements with high electron affinities. If atoms belonging to these two different groups, metals and nonmetals, are allowed to react, chemical bond is formed. This type of chemical bond, which is formed due to complete transfer of electron from one atom to another atom, is called ionic bond. The formation of NaCl is a good example of this type of bond. Sodium chloride is a simple compound formed by sodium Z equal 11 and chlorine Z equals 17 atoms. The ground state of electronic configuration of these elements is shown as below. The frames indicate electrons in the valence shell of these elements. Sodium has only one electron and chlorine has 7 electrons. Sodium, being electropositive element, has the tendency to tendency to lose electron, and chlorine, being an electron activity element, has a tendency to gain electron. Therefore, they form positive and negative ions by losing and gaining electrons respectively. They attain electron configuration to the nearest noble gases. By losing one electron from the outermost shell, sodium becomes Na plus ions ion, and it is left with 8 electrons in the second shell, which will now becomes the valence shell by gaining one electron. Chlorine atoms now also has 8 electrons in its outermost shell and becomes chlorine ion. Both of these atoms are non-changed into oppositely charged ions. They stabilize themselves by combining with each other due to electrostatic force of attraction between them, such as it is to be noted that only valence shell electrons take part in this type of bonding, while other electrons are not involved in such type of reaction. Heat is usually given out. The compounds formed due to this type of bonding are called ionic bond, covalent bond. Covalent bond. The elements of group 13 to group 17, when allowed to react with each other, they form a chemical bond by mutual sharing of their valence shell electron. This type of bond, which is formed due to mutual sharing of electron, is called a covalent bond. The energy changes during the covalent bond formation are of considerable value when two atoms approach to each other. Attractive forces develop between electrons of one atom and nucleus of the other atom. Simultaneously, repulsive forces between electrons of the two atoms as well as between their nuclei are also created when the attractive forces dominate due to decrease in distance between those two atoms. A chemical bond is formed between them. The formation of hydrogen, chlorine, nitrogen, and oxygen gases are few examples of this type of bonding. Types of covalent bonds, as described above, the covalent bond is formed by mutual sharing of electron between two atoms. The electrons that pair up or to form a chemical bond are called bond pair electrons. Depending upon the number of bond pairs, covalent bond is classified into following three types. Single covalent bond. When two electron is contributed by each bonded atom, one bond pair is formed and it forms a single covalent bond. While drawing the structure of such molecules, the single bond pair is indicated by a line between those two atoms. A few examples of molecules with single covalent bonds are hydrogen, chlorine, hydrochlorine, acid, and methane. Double covalent bond, when each bonded atom contributes two electrons, two bond pairs are shared and a double covalent bond is formed. These bond pairs are indicated as double line between those atoms in the structure of such molecules. The molecules like oxygen, gas, and ethane show such type of double covalent bond. Triple covalent bond, when each bonded atom contributes three electrons, three bond pairs are involved in bond formation. This type is called triple covalent bond. Three small lines are used to indicate the three pairs of electrons between those atoms in the molecules of such compounds. The example of molecules having triple covalent bonds are nitrogen and ethene. By this mutual sharing of valence shell electrons, each of the contributing atoms attains the octet or nearest noble gas electronic configuration. That is covalent or coordinate covalent or additive covalent bond is a type of covalent bonding in which the bond pair of electron is donated by one bonded atom only. The atom which donates the electron pair is called donor, and the atom which accepts the electron pair is called acceptor. A small arrow is usually used to indicate the atom and pair of electron being donated. The head of arrow is towards the acceptor atom. The non-bonded electron away electron pair available on an atom like the one available on nitrogen in ammonia is called a lone pair. When a proton approaches a molecule with the lone pair of electrons, the lone pair is united to H and a hydrogen and a coordinate covalent bond is formed for example, formation of ammonia radical. In the formation of boron trifluoride molecules, three valence electrons of boron atom that is 5 pair up with three electrons, one from each three fluorine atom. The boron atom even after this sharing of electrons, covalent bond formation remains short or defecate of two electrons in its outermost shell. Now, if a molecule with a lone pair approaches this molecule, it accepts lone pair from that donor and forms a coordinate covalent bond. The lone pair on nitrogen of ammonia molecules makes it a good donor molecules to form a coordinate covalent bond as shown in figure. Polar and non-polar covalent bond. If a covalent bond is formed between two similar atoms, homoatoms, the shared pair of electrons is attracted by both the atoms equally. Such type of bond is called non-polar covalent bond. These bonds are formed by equal sharing of electron pair between the two bonded atoms. This type of bond is called a pure covalent bond. For example, bond formation in hydrogen 2 and chlorine. If the covalent bond is formed between two different types of atoms, heteroatom, and then the bond pair of electrons will not be attracted equally by the bonded atoms. One of the atoms will attract the bond pair of electrons more strongly than the other one. This atom element will be called as more electronegative when there is difference of electronegatividity between two covalent covalently bonded atoms. There will be unequal attraction for the bond pair of electrons between such types. It will result in the formation of polar covalent bonds. The difference between electron activities of hydrogen and chlorine is 1.0. As the electron activity of chlorine is more, it attracts the shared pair of electron towards itself with the greater force. A partial negative charge is therefore created on chlorine and in turn a partial positive charge on hydrogen due to electron activity difference. It creates polarity in the bond pair and is called polar covalent bond. The delta sign indicates partial positive or partial negative charge that is developed due to unequal sharing of shared pair of bonded pair of electrons. The compounds resulting from polar covalent bonds are called polar compounds. For example, water, hydrogen fluoride, and hydrogen chloride. By using electronegativity's values, it is possible to predict whether a chemical bond will be ionic or covalent in nature. A bond formed between elements of high electronegation halogen group and elements of low electronegation alkaline metals are ionic in nature. There is complete transfer of electrons between them. The bond between elements of comparable electronegativities will be covalent in nature as the bond between carbon and hydrogen in methane or nitrogen and hydrogen in ammonia. If the difference of electron activities between two elements is more than 1.7, the bond between them will be protometally ionic bond, and if it is less than 1.7, the bond between two atoms will be protometally covalent. The metallic bond is defined as a bond formed between metals atom positively charged ions due to mobile to free electrons. The different properties shown by metals such as high melting and boiling point, good conduction of heat and electricity, hard and heavy nature suggested extents of different part of chemical bond between atoms of metals. In case of metals, the hold of nucleus over the outermost electron is weak because of large size atoms and greater number of shell in between nucleus and valence electrons. Furthermore, because of low ionization potential, metals have the tendency to lose their outermost electron easily. Resultantly, these lower free electrons of all metal atoms move freely in the spaces between atoms of a metal. None of these electrons is attached to any particular atom. Either they belong to a common pool or belong to all the atoms of that metal. Nuclei of metal atoms appear either in say of these free mobile electrons. These mobile electrons are responsible for holding the atoms of metals together, forming a metallic bond. A simple metallic bond is shown in figure. Intermolecular forces, as discussed earlier, the forces that hold atoms in a compound are chemical bonds. In addition to these strong bonding forces, relatively weak forces also extend in between the molecules, which are called intermolecular forces. The bonding and intermolecular forces of hydrochlorine acid are shown below. It requires about 17 kJ energy to break these intermolecular forces between one mole of liquid hydrogen chloride molecules to convert it into gas worth about 413 certain kJ energy required to break the chemical bond between hydrogen and chlorine atoms in one mole of hydrogen chloride dipole and dipole interaction. All intermolecular forces, which are collectively called van der Waals forces, are electrical in nature. They result from the attraction of opposite charge, which may be temporary or permanent. The unequal sharing of electrons between two different types of atoms make one end of molecules silently positive and the other are silently negative charged. As shared pair of electron is drawn towards more electronegative atom, it is partially negative charged as chlorine in hydrogen chloride. The other end automatically becomes partially positively charged when partially positive and partially negative charge exist in a different position in a molecule. The adjacent molecules will arrange themselves in such a way that negative end of that molecule comes near to positive end of other molecules. It results in a net force of attraction between oppositely charged ions of two adjacent molecules. These attractive forces are called dipole attraction. Interactions are represented in HCl. Hydrogen bonding. Hydrogen bonding is a special type of intermolecular forces present in the permanently polar molecules. This bonding can be considered unique. Dipole attraction. This force of attraction develops between molecules that have a hydrogen atom bonded to a small, highly electronegative atom with lone pair of electrons, such as nitrogen, oxygen, and fluorine. The covalent bond between hydrogen atom and other atom becomes polar enough to create a partially positive charge or hydrogen atom and a partial negative charge on the other atom. The small size and high partially positive charge on the hydrogen atom enables it to attract highly electronegative nitrogen, oxygen, or fluorine atom of the other molecule. So partially positively charged hydrogen atoms of one molecule attract and form the fluorine with the partially negative charged atom of the other molecule. The bonding is called hydrogen bonding. This force of attraction is represented by a donated line between the molecules as shown below. Hydrogen bonding affects the physical properties of the molecules. Due to this, boiling point of the compound are affected greatly. For example, boiling point of water 100 degree is higher than that of alcohol 78 degree because of more and stronger hydrogen bonding in water. The important phenomenon of floating of ice over water is because of hydrogen bonding. The density of ice at 0 degree 0.917 is less than that of liquid water and 0.0 degree 1.00 in the liquid state. Water molecules move randomly. However, when water freezes, the molecules arrange themselves in an order from that gives them open structure. This process expands the molecules that result in ice being less dense or compound water. Nature of bonding and properties. Properties of the compound depend upon the nature of bonding present in them. Let us discuss the effect of nature of bonding on the properties of compound. Ionic compounds. Ionic compounds are made up of positively and negatively charged ions. They consist of ions and not the molecules. They positively and negatively charged ions are held together in a solid or crystal form with strong electrolytic attractive force. The orderly arrangement of sodium and chlorine ions in a solid crystal of sodium chloride is shown in figure. The ionic compound have following properties. Ionic compound are mostly crystallized solid. Ionic compound in solid state have negligible electrical conductivity, but they are good conductor in solution and in the molten form. It is due to presence of free ions in them. Ionic compounds have high melting and boiling point. For example, sodium chloride had a melting point 18 degree and a boiling point 1413 degree. As ionic compound are made up of positive and negative ions, there exist strong electrostatic forces of attraction between oppositely charged ions, so a great amount of energy is required to break these forces they dissolve easily in polar solvent like water. Water has high dielectric constant that weakens the attraction between ions. Covalent compound. The covalent compounds are made up of molecules that are formed by mutual sharing of electrons between their atoms. Covalent bonds. A covalent bond is generally regarded as weaker than an ionic bond. Covalent bonds are made up of two or more non-metals, hydrogen, lower molecular mass. Covalent compounds are gases or low boiling and liquids. The contrary to it, higher molecular mass. Covalent compounds are solid. Generally, properties shown by covalent compound are as follows. They have usually low melting and boiling point. They are usually bad conductor of fluidity. The compound having polar character in their bonding are conductor of fluidity when they dissolve in polar solvent. They are usually insoluble in water but are soluble in non-aqueous solvents like benzene, ether, alcohol, and acetone. Large molecules with three-dimensional bonding from covalent crystal, which are very stable and hard. They have very high melting and boiling point. Polar and non-polar compound, as discussed earlier, the polarity in a chemical bond is due to difference in electron activities of the bonding atoms. On the Pauling scale, fluorine has been given an electron activity value of 4.0. The values for other elements are calculated relative to it. Properties of nonpolar and polar covalent compounds differ to some extent. Nonpolar covalent compounds usually do not dissolve in water, while polar covalent compounds usually dissolve in water. Similarly, nonpolar compounds do not conduct electricity, but an aqueous solution of a polar compound usually conducts electricity due to the formation of ions as a result of its reaction with water. Coordinate and coordinate covalent compounds. Their properties are mostly similar to those of covalent compound, as the nuclei in these compounds are held by shared pair of electrons. Therefore, they do not form ions in water due to their covalent nature. They form solution in organic solvent and are very less soluble in water. Usually, they are rigid compounds without dipole. Metals have common property of conducting heat and electricity. It gives them prime role in many industries. Major properties shown by the metals are as follows. They show metallic luster. They are usually malleable and ductile. Malleability is the property of which a metal can be rolled into sheets, while ductility is the property by virtue of which a metal can be drawn into wires. They have usually high melting and boiling point, being greater in size. They have low ionization energies and from cations very easily. They are good conductor of heat and electricity in solid and liquid state due to mobile electrons.